Okay, 6 o'clock. Let's get started while others are joining in. So today we are supposed to do the second half of your this assembly MIPS assembly learning, which basically uh, concentrate on the branching and looping and those things. Uh, and we also had this problem of understanding this machine code generation for the branchings and the looping with respect to our addressing modes like pseudo addressing, PCL relative addressing, and so on and so forth. So I hope you guys did try that problem I given last time. So let me go through that and then you can see whether it match your results or match your steps and understanding. Okay, so any question before we go into those problems with? Okay, all right. So let me share my screen. Okay, okay, so if we review the previous one, uh, the first problem was like these so what we claimed last day, this immediate field is basically giving you the number of instructions offset. It is not really the address offset, it is the number of instructions you need to jump forward or backward. And then we had to understand what is that number of instruction to jump forward or backward relative to, whether it is that current instruction where the BNE is, for example, or if it is the next instruction with respect to what it should go jump there. So let's review this in a little bit more of the abstract sense. It's so let's say we have like 10 instruction in our hand with this a couple of labels there, L1, L2, and L3. So we have these 10 instructions, and let's say these instructions are placed from address 0. Okay, and we'll use that just for make our life simple. We will use decimal number system for the address, not the hex. Okay, so let's put the addresses there. So first instruction is placed at 0 address. Then the next instruction should be placed at 4, right? Because each instruction is 32-bit, which is 4 byte, and it's a byte addressable memory. So we'll add 4 on top of that. Next will be 8, then 12, then 16, then 20, 24, 28, 32, and 36. Also, let's assume this. Let's assume your I3 is at level 2. This instruction 3 is causing like a branching here, like somewhat like B equal or something. Okay? And I7 is branching to L1. PC relative branching, that's a BNE, something like that. Okay. In this case, what is going to be my immediate value? So we can actually compute the machine code. Like so, we know that machine code for BNE or B equal would be similar to this, right? its registers and an opcode and some immediate value. So we are more interested in this, computing this, what is going to be here. And we know, like if I just share this page with you, see the BNE or B equal has BNE, where is it? Here. Is that PC equals PC plus 4 plus the branch address. So we discussed that this PC is like PC new is PC current plus 4 plus the branch address. So branch address would be this, like it's basically taking the immediate bit appended with 2 of 0 and then sign extend that immediate value. So what does it signify? So it's, let's say branch address, let me just write down the branch address there. Branch address was 14-bit of immediate MSB followed by the immediate followed by 2-bit of 0. Okay. So this part we understand, like it's a sign extension, means basically is converting like 16-bit values to the like 32-bit values or 30-bit values, whatever it is, and preserving the sign of that value. So it's both preserving sign and magnitude of the value. That part we know. Now what is this part? This part is what? It is basically, isn't it, like immediate equals immediate left shift by 2-bit, right? So this operation, immediate equals immediate left shift by 2-bit, will give this extra 2-bit 0 at the LSB side of that bit pattern. And now what is this? Isn't it this one multiplied by 4? So remember, if anything is multiplied by power of 2, we can actually left shift that much amount, that much power, right? If it is something like some A equals A multiplied by 2 to the power 16, it is same as A equal to A left shift 16, right? So with that understanding, we know that this is immediate value multiplied by 4 from this understanding. Question? Okay, now we see that we always compute the new address based on the next instruction address. It is not the current instruction, the next instruction. So we can, let's assume that we can actually want to compute that how many instruction ahead or we want to jump. Like in this case, it would be with respect to I4, because I3 is that B equal instruction we are assuming, and since we need to compute with respect to PC current plus 4, so my PC current is 8, so PC current plus 4 is 12. So my relative position of the jump instructions should be determined from I4, and which is basically, this is like from here 1, 2, and 3. So what we can do is basically, let's assume like this is the case with respect to that we are computing. So PC current is, in this case, is 8 plus 4 plus immediate, we are assuming this is 3 multiplied by 4. This is like 12 plus 12 equal to 24, which is exactly the instruction address of the instruction where we want to land with this BEQ, right? So for the forward jumping, this assumption is working fine, that we need to calculate with respect to the next instruction. Now, how about the other way? That when we want to go and jump to the previous instruction. So let's do that. So with that respect, let's say I want to jump from here with the BNE, go back to there. So my PC plus this thing, 4, is practically my I8, right? So that means I need to jump back like 1, 2, 3, 4, 5. So in this case, my calculation would be my current instruction, PC current is 24 plus 4 plus, remember, we are going back into that sequence of instructions. So it has to be minus 5 multiplied by 4, which is equal to 28 minus 20 equals 8, which exactly is where we want to land in, or from which address we want to pick up that instruction with the BN. Wait a minute. No, we want to jump on the L1. So a little bit more computation. 6. This is 6. This is then become 24. This become 4. Okay, so our new thing is here. So we jump back to the 4, instruction 4. That's where we want to be, right? So that means our actually understanding that we need to count with that how many instruction we want to go forward or backward. It has to be with respect to the next instruction of that corresponding BNE, BEQ, that kind of instructions. Question?
So why do you have to plus 4?
PC current plus 4, you mean?
Yeah.
Okay, that's a good question. Let's wait for 147 to come up. Okay, so it's internal to the processor. Okay, so that's a question, good question. Hold on to that question, and hopefully in 147 you will get that answer. So it's by the hardware choice, like by the hardware construction, it is like that. Now, unless we review the hardware construction inside the processor, how it works, then we won't be able to understand. So that's the scope of 147. Okay, so right now for this class, we just assume by the hardware construction, we have to do that, PC current plus 4. Other question? Okay, then how about this problem? Now we have this understanding, and let's look at this problem. And let's concentrate on this BQ and try to find out what's the machine code of this going to be. Okay, so let me try to erase this from here. Okay. Now we see that we have this equation, right? PC new equals PC current plus 4 plus my immediate value multiplied by 4. Now for this one, we know the PC new. We know the PC new because PC new is going to be, if it goes all the way here. So this is your PC new, right? And PC current is basically this one, what this BQ instruction is, at which address. So that means we have this PC new is 1001.001C. PC current is X1001.000C plus 4 plus immediate multiplied by 4. Okay, these 4 are decimal 4. Okay, so that means we just got a plain old equation we need to solve, and this becomes like what? Like if you just bring over this term to this side, it becomes like 1C, oh no, 10 equals 4 plus immediate multiplied by 4. This implies, this is basically 10 is 16 in decimal. Okay, so this is 16 in decimal. 4 multiplied by immediate implies 12 equals 4 multiplied by immediate implies immediate is 3. All right, so we know the immediate is 3, and all now we need to do is to construct that machine code, right? This is my format, RSRT, and opcode for that it's a BEQ, right? BEQ opcode is 4 hex. Opcode is 4 hex. So that means my opcode is going to be, that is 6-bit, remember? Then RS and RT. So which one is RS, which one is RT? This one is RT, this one is RS. So RS is, okay, we need to place RS RT by the format RSRT. Okay, my RS is S0. S0 is 16. S0 is 16. So let's just note down the values here. This is 16 by decimal, I'm writing there. And RT is S1, which would be 17. And immediate field is 3. Now it's just a matter of putting the bits onto there. So 6-bit, 5-bit, 5-bit, 16-bit. So that means this 6-bit 4 means it is 0, 0.
Professor, could you repeat how can you get 4? Because immediate 3 is, I think, C in a chart is C hex or 4 hex. I don't know how to get, how do you get it?
Oh, wait a minute. Come up with a question. What is that?
Immediate is 3. When you look at the chart, is C, or am I wrong? I don't know.
Immediate is C in the chart.
You got it. Immediate is equal to 3. Okay.
Yeah.
So when you look at the chart, you got a 4. How?
No, this is the immediate. This chart is opcode.
Oh, this chart is opcode. Okay, okay.
This is opcode to opcode. This is nothing to do. They don't go about the immediate field or anything, right? It just
Okay.
the opcode. So yeah. Um,
Sorry.
hey, no problem. So this is like 6-bit, right? So 40100, right? Am I right? 1, 2, 3, 4, 5, 6. Yeah. So this is your opcode. Then RS would be 16 in a 5-bit. 16 in a 5-bit. Simple 10000, right? 1, 2, 4, 8, 16. Yeah. 17 10001 in a 5-bit position, and 3 in 16-bit is 0000000000000011. So this is your machine code in binary. Machine code in binary. And then this thing, your hex code, how it's going to be, we'll just group it with respect to the 4 bits from the MSB side. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So it's going to be 1, 2, 1, 1, 0, 0, 0, 3. So hex code for this instruction be equal, this exit is going to be 1, 2, 1, 1, 0, 0, 0, 3. Question?
So I tried that out in Mars, and it seems like Mars flips the RS and RT around. So because the machine code, when you do that instruction in Mars, has the 17 first and then 16.
17 first and 16. Okay. Uh, yeah, it actually depends on what this sequence is going to be. I think, okay, I think that's a good point you brought. Actually, we need to check here the branch equal instruction, what it basically do for. Okay, so branch equal, let's look at that. Oh, here. So this assembler actually assume RSRT for the BNE code. So probably B equal is the similar one. Let me see. Yeah, okay, okay. Thank you very much for bringing that into attention. So yeah, so we need to look at to that. Like we were, I was kind of assuming this is the case, but seems like for the B equal, this is the opposite sequence. We first go with the RS and RT, so that means these will be swapped, 17 and 16. So these patterns, I think, yeah, these patterns will be swapped around. So yeah, thank you very much for that note.
I had a question though. Where did you see that in the green sheet?
What's that?
That B equal puts RS and then RT.
Yeah, it's not much specified on that green sheet as a whole. Like it is more like this is from the hardware perspective. It is saying that it does not consider anything on the assembler instruction side, how that format would look like. It doesn't want to impose that, and that comes from here basically. Let's look at the other I-type instruction. Is it the same or the different? Yeah, see, the arithmetic operation has this RTRS convention, right, for the immediate instructions, but apparently the BEQ has a different sequence or different meaning for the assembler at least. So that's why. So for us, yeah, we need to actually look at exactly what BEQ format is from this document and place that RSRT accordingly. Okay, so this would be, let me just refresh, this would be RS, this would be RT, so this would be 17, 16, and then we need to adjust a bit accordingly here. Okay.
So I had a question about when you said the arithmetic operation. So I guess, for example, because add immediate says it's R register RT is equal to register RS plus sign extension immediate. Does that mean that RT is coming first in this case?
So in this case, the assembler form, like if you do an add I, $T0, $T1 immediate some value, then that $T0 is basically your RT and $T1 is RS. Make sense?
And then for the branch equal to, branch on equal, is it because like they said like in the if statement, the register RS is equal to register RT. So I guess in this case, they're putting RS first.
Right. So in this case, if you are doing like this one, right? In this case, if you are doing like,
Oh.
right, if in this case we are doing like B equal S0 S1, so S0 is exactly my RS and S1 is exactly my sorry, S1 is my RS and S0 is my RT. No, not clear?
Oh yeah, I see. I guess it's more clear on the lecture
Yes,
material.
yeah, this one you are adding, let's say add I S1 S0. So S1 should go in the RT field and S0 should go in the RS field, right? In this case. Here the same sequence, B equals S1, S0. Now S1 needs to go in the RS field and S0 needs to go in the RT field. So it is just by this convention that assembler is following.
Okay, yeah.
Oh, Professor, I just
Yes.
wanted to, I forgot, like, what does RT stand for? I guess RS is a source register, right?
RS is like source register,
And then what does RT stands for?
is a target register.
Target register. All right, thank you.
Okay, then if we don't have any other question, let's move on to the other part, like this one, jump loop. Okay, jump loop. So let me use, let me see if I can copy this text. Let's see.
So, Professor, if we were to have the same question in the quiz, do we go with the like Mars, like how Mars has the format of a target and source register?
Yes, please.
Okay.
Yes. So we need to consider this information as well. Okay.
All right.
And if that, if there is any discrepancy in the results and stuff like that, just communicate with me after the quiz or after you get the score.
All right. Thank you.
Okay. So yeah. Okay. So now let's work on this jump. Okay. Now let's work on this jump. So we want to work on the jump J loop. Okay. So for this one, what our what is this page is saying. So for the jump, it is a jump address, and jump address is constructed with a PC plus 4, and we take the upper 4 bit of it, followed by the address, that 26 bit, and followed by 2 zeros. So that essentially it means that like this. Let's say my PC current plus 4. Okay, PC current plus 4. What is that quantity? That quantity is this one, right? My PC current is this. I'm executing this instruction. So current plus 4 would be this one, which is like 01101 001C, and which is, I can write down like this. If I just expand it to the 32-bit quantity, which is like 0 0 0 1 0 0. Let me use a different ink there. 0 0 0 0 0 0 0 0 0 0 0 1 0 0 0 0 0 0 0 0 0 0 0 1, and C is 1 1 0 0. Okay, so this is the 32-bit pattern if we expand PC current plus 4. And my PC next. So let's look at the PC next. So PC next is going to be J loop. So this is looping here, right? So I'm going to pick up this address. So PC next is going to be my 0101 000C. Okay. So what I do here is basically, let me just write down, expand it. So this one is here. And if I 32 expansion, bit expansion, this becomes like this. 0001. Okay. Then let me change the ink. 0000 0000 0001 0000 0000 0000 1 1 0 0. Okay, so that's going to be my PC next. Now let's again review what this page is saying. Let me see. Okay, this page is saying, can I drop this font? Okay. Is a PC plus 4 and take the 4 bit out of it. So which means you take this 4 bit and then followed by the 26 bit and automatically prepend 2 zeros. That's how we are going to construct this, right? So basically that means my immediate field, sorry, jump address, J address, that 26 bit is going to be this, exactly the one with the yellow ink, right? One with the yellow ink. So if I have my opcode, for J is jump 2 hex, okay, 2 hex. So on the 6 bit, it is 0, 0, 0, 0, 1, 0, right? This is 2. And then I write this 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1. This is 26 bit, right? 4, 4 plus 4, 8, 12, 16, 20, 16, 20, 24, 26. So this is 26 bit. So practically what we are doing, we are basically bringing this pattern onto this jump address field. So to determine a jump loop instructions machine code, what we need to do, we need to look at this PC current plus 4, that address, blow it up, okay? And we know we are going to take, or hardware is going to take the upper 4 bit of this value, and then it will join this 26 bit and prepend zeros automatically to build the PC next address, which is my target address. So we lay down the target address value, we already know that. Then we cut out, okay, then we throw these MSB 4 bit and LSB 2 bit. We throw it away, and rest 26 bit, we basically put it on the, in my jump address code. So given this jump address code, now the hardware, what it will do, it knows my PC current plus 4 value. So it will pick up that 0, 0, 0, 1. So when it is executing, so when microprocessor is executing this code, this instruction, whatever that is, like in a hex or whatever, this microprocessor process the machine code anyway in the binary form. So it's executing this instruction. It exactly look at this PC current plus 4, pick up the most significant bit, then picks up the jump address field 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, and then append 2 zeros on top of that. And that is how it construct the next address and execute that instruction. So as if it is jumping and executing to that instruction. Question?
Professor, well, what is the need for taking out the least significant bits and then re-adding them? Is this like how the hardware works, or is there a special reason to it?
That's a good question. So you see that in the jump address, I can pack 26 bit, right? That's by the format, because my opcode is 6 bit field always, and only rest of them 26 bits are dedicated for the jump address. Now let's say we want to allow like all these other, like we don't actually go and throw these two, right? And want to allow these 2 bits here. That means my range of jumping is actually, we are shrinking it down. With respect to, why? With respect to, if you see all these addresses, instruction addresses, all of them has these 2 LSB field 0, 0, always. Like if you like expand all these addresses, you'll see all the instruction addresses, LSB 2 bits are always 0. Why? Because each instruction is 4 byte long, right? So each instruction is going to occupy 4 addresses, 0, 1, 2, 3. So next instruction will be starting from 4. Next instruction will be starting from 8. So every addresses are divisible by 4. That means your last 2 LSB has to be 0, 0. It's always, right? So with that, we don't need to pack this information at all. Like we know this is going to be 0, 0. And that's what makes our jumping scope bigger. That's the reason.
Oh, that's pretty smart. Oh yeah, now I get it. And another question, Professor. So but the hardware does store the most significant bits from the left side, right? Like it does keep track of that.
Means from the PC current plus 4, you mean, for that
No,
one?
in the where yeah, this one.
Yeah, yeah, it has a storage. That is the program counter register that is being already storing these values. So it knows these 4-bit always, the
So
higher 4.
this is the only way to access program counter. I mean, like we can't really edit it like in any other way, right?
No, no, we cannot do anything. Like it's basically indirectly altering the program counter, right? We need to alter the program counter anywhere, like to do the like branch on equal, branch on not equal, do the jumping. These are all manipulating the PC. But what we cannot do is something like add $PC $4, like increase the PC4. We cannot do that. It is not permitted.
Yeah. And
It's only that we put some instruction like BNE, BAQ, and while processor executes that, the whoever is controlling this whole wide computing world inside the processor, it decides, okay, hey, for this instruction, I need to go and change the program counter value. Then it goes and changes. So as a programmer, we cannot directly change it.
so Professor, we had a question in the quiz where it asked us to give the size of memory file register file in in MIPS. So when we calculate the register file size, like do we consider the
No,
special purpose register as well, like
no,
PC
register
or
file is the general purpose registers.
okay? So like we have a different file for special purposes.
Uh, there are only few special purpose registers. They are not like collected into one single like area. So,
Okay, so
so
they just
hardware
like
point of view, like registered file has a different hardware structure than all other special registers.
okay. Thank you, Professor.
No problem.
So
Yeah.
I suppose normally the text um, section of the addresses would start from like 0040 up to like
Hmm.
1000.
Right.
So I suppose like you wouldn't be able to test this in Mars because
No.
it seems like when you try and start text at outside that address range, it doesn't let you.
Right. Right. So you can try it with the normal address like 0040. Start from that address. That will only change your upper half of the addresses. Like all your lower half will be the similar. So it won't actually affect at all your let's say, yeah, it won't have affect your this thing or your this code
Um,
most. That's my
it,
feeling.
it does seem to change the in that third block, the zero
Yeah,
zero
yeah,
zero
yeah.
one.
Of
It
course.
changes it to
This is
0100.
this will change your machine code already. Yeah, machine. This will change your machine code basically. At least for the pseudo instruction. Pseudo instruction deals with the part of the address, so it will change your machine code in the sense this guy is just thrown out anyway. Yeah, this guy will be changed. These 3 fields will be changed accordingly. Yeah, you are right.
All right, okay.
Professor, why would be they be changed again?
Was it?
Like, so we agree that they will be changed, like, but why will we change them?
Oh, means on the marks on the real program.
Yeah.
So I just give you a theoretical scenario here, right? So that you have to do it on the paper pencil. Like no one can just cut paste this program and get a result out of it.
Okay, all right. All right.
Yeah. So you are all forced to do a paper pencil evaluation and make machine code out of this. That's the one reason, definitely. Okay, let's take a 5-minute break at this point. About 6:50, we'll be back then. Okay, let's get back and yeah, continue with the discussion. Uh, so I'd like to show you a couple of guidelines and like tips to do an easy assembly program. The philosophy here is we all are used to the high level programming, right? So when it is given, uh, basically when it is given a like a problem to solve, a big problem to solve, we tend to think in terms of the high level language, whatever you are comfortable with, like either Java or Python, C, C++, doesn't matter. Uh, then can we actually solve the problem at that level, and can we systematically go and implement at the assembly level? That's the process I'd like to show you with a simple example like this. Let's say we are thinking a program like this, like a high level program, and how can we write the corresponding low level code? Now to do that, let's concentrate on this piece of things, right? These other variable, etc., will come later. But how can we do this one in the assembly level? Because you know that assembly level program doesn't have a concept of the code block like what you used to do within curly braces and separate the code block and execute on different conditions, true or false evaluation, execute this block or that block, etc. Assembly doesn't have it. So everything has to be done through labeling of the statement. So in C, language C, there is a go-to statement. I'm not sure if Java has a go-to statement, but C has a go-to statement, and it follows with a label of a specific C statement into the program. So I tend to think in terms of that. Can I convert this piece of code in terms of go-to if then and go to statement, and if I can do that, then it will be easy, straightforward conversion to the corresponding assembly language. So let me show you that, like what I mean. So let me pick up another text. Okay, so from here, if I just write it down like this, if A greater than B, then go to L1. Okay, then C equals B minus A, and okay, go to L2, L1 is C equals A plus B, and then B equals A multiplied by B, whatever that program is. So here in this case, if you see, we have this block of logic just reversed, right? Just reversed. So you see this one is basically coming over here, and else code is going over there. So how it works, it basically tests if A greater than B, then jump to the level 1, perform this, and then this. So it is exactly the same as a high level code is doing, right? If it is greater than B, perform the addition, and then perform this one. Don't even go here. But in this program, if it is not there, then go and fall behind the else part and then bypass this code, right? So we need to do a L2 here. So that means I need to go and, okay, hold a minute. Make this a level L2. L2. Okay. Now this code is complete. And of course, we can actually have this other statement. C, Control P. Okay. Now, yes. Now I want to call it an intermediate high level code, intermediate code, I would say. Intermediate code. Now from here, my thought process is this. First, we establish a map like, okay, my high level variable, I will use, let's say T0. B, I'll use T1. C, I'll use T2. But let's change the scenarios, S2. Okay, just arbitrary, no logic. So I choose that. So that means this part of code is actually calls for load immediate. A is T0, right? T0, 10. Load immediate B is T1.
Professor, why you choose temporary for A and B?
Just like that. No logic. You can choose anything.
Okay.
Unless you are calling a function after that, we'll be going to the function concept next lecture. Then you need to consider what you need to store and what you don't need to store, and etc. etc. Oh, sorry, means what you need to preserve and what you don't need to preserve. Those concepts will come in next lecture, but right now, not important that much. So this will be your first initial part of this coding, right? This initializing these registers, and then start with, okay, let me just do some spacing here. Then start with this thing, right? If A greater than B, there is a BGE, BGT. Yeah, BGT, that's a pseudo instruction, but we can use it. BGT A greater than B, right? So it is probably T0 greater than T1. T1. L1. The next one, so this one is this, right? So this one is this. And next one is a sub. The result is in C, which is S2, B minus A. So it is T1, T0. So this one is this. Yeah, and then go to L2, which will be jump L2, and then L1 is add $S2, $T1, or $T0, $T1, and L2 would be mult dollar, okay, B is T1, AB, T0, T1. So that would be your, like, now you see, like, as soon as I change it in an intermediate code with the goto, and jump instead of code blocks, it actually is a straightforward conversion into the assembly, right? Question? Okay, then let's try to do one more, like a loop. This is a decision making.
Professor, I have a question.
Yeah.
So, like in a high level code, like is there any overhead cost when it comes to like performing these operations, like in terms of speed? Like will like lower language will be a faster code or they be the same?
Uh, to answer your question, we need to review how this upper level code gets turned into the machine code, right? We all understand by now that machine does not understand upper or high level codes at all. It is the compiler and assembler actually converts these high level code written into the machine code. Now that conversion process has its limitation, and it actually try to exploit more of these generic function and implementation. So that means if we really want to optimize a piece of code, which is very critical, especially it is applied onto your real-time system, real-time operating system, where the response time or code execution time is very important, their critical parts are done at the assembly level, exploiting all the special functionality there. Now, saying that, compilers are getting smarter and smarter. So it basically, if you look at the C++ compiler especially, they have this all these optimization level. Like it starts from 0 to I think it's 5 or 8. I don't forget that exactly how much optimization level this has. But different optimization level actually try to exploit these hardware capabilities to make the code faster. But again, this is algorithm. This is a human program written to convert high-level conceptual code into the low-level machine code. So there will be always a scope to optimize directly at the assembly level. Make sense?
Yeah, it does. Yeah, thank you.
Okay. So let's pick up this example now. Okay, so this is my high-level code. Okay, just to complete this one, let me just put assembly code. Okay, so this is my high-level code. Now my goal is to translate it into my this code with a with this if, go to, etc. Like there is no while or nothing in the high level, sorry, low level assembly level code. So we will try to avoid them in this intermediate level code, writing that. So while is basically saying that if I less than equals, or okay, reverse the logic. Okay, reverse the logic. The logic here is I less than equals a. You go and execute this. I'm going for an exit logic here at this point. So that would become like if I greater than a, go out of loop, go to L1, and then you have s equal to s plus I, come to s plus I, then I equals I plus 1, then go to, let's level it. Okay, let's make it L1, and let's make it L2. go to L1, and L2 is S equals S equal to S plus, S equals S multiplied by A. So that's the program at the intermediate code level, right? That is the program at the intermediate code level. So what is the correspondence? The correspondence is my while is turned into an if. Then this goes here. This is my block in the loop. And then this one goes here. So that means together, this statement and this statement, it is basically making the while loop. So once we have this, then it's basically just straightforward, right? It's let's put a map. Let's say A equals T0, I equals, let's say T1, S equals S1, let's say. So that means writing these would be like this. Li, let's press 2, 3, 4. Li is T0, right? T0, 10. Li T1, 1. Li S1, 0. And then L1 is BJT I, which is T1, A, which is T0, to L2. And S equal to S plus I, which is add S is $S1, $S1, I is $T1, add I, so I equal to I plus 1, I is $T1, $T1, 1, jump, that go to L1 is jump L1, L2 is your multiplication, right? Mult S $S1, $S1 with A, $T0. So that becomes your assembly level code. And it is, again, like if you see, it is straightforward from the intermediate code. So this guy goes here, this guy here, this guy here. So this has exactly one-to-one correspondence with the intermediate code. So while doing the programming, I'd recommend, like when you solve these other complex problem in the programming assignment and in the project, try to think from a high-level code perspective, then change it to the intermediate code, like this with the if and go to, etc. And from there, your life will be easier to write that piece of code for you. So that is one recommendation. The other way is also true. Other way also true means if a given piece of code is given to you, you basically look at this code and convert back into the intermediate. You can just convert back into the intermediate code like this, right? Just do a reverse mapping and convert into this code, and from there you can actually either understand what this code is doing better, like if you write in a high level form, yet if you can actually manage to, you can also manage to go into the very high level code from there. and there you can actually follow through what a piece of given code is doing. So if you are given a piece of code and you need to understand that, I would recommend to follow this process, like reverse process. From the assembly code, make some at least some intermediate code to understand the top level concept, or at least top level thinking what that piece of code is doing. Question?
I had a question about a label, like, for example, what
Yes.
if this like while loop was the very last thing in your machine code.asm file, and then you didn't have that last multiplication step? Could you like just put an L2 label at the very end, and even though there's no instruction to attach it to?
Oh, okay. So yes. So basically you can make a label, but at least what I recommend, it has an exit code from there, right? At least from our Mars, we have this exit macro always, right? Do at least place an exit.
Oh, okay, that makes sense.
Yeah, otherwise try putting L2 just without any code and experiment that and let us know what it do. That's a good point actually. If there is nothing after the while loop, how should we handle that part? That's a very, very good question. So please do an experiment. Just put a blank level there in the code and see how Mars handle it. Okay, so what else?
Professor, when will be the answers posted to the quiz?
Oh, that one. I need to see. There is one student I'm considering to give some extension, so that's why I'm not making this up. But yeah, definitely it will be before midterms for your studies.
Okay.
Yeah, that's for sure. But I'm just delaying it for one case that I still probably that person needs an extension depending on the situation.
Okay, so that will be for both of the quizzes, right?
Yes, both of the quizzes. Yes.
Okay. All right. Thank you.
Okay, I'll work on that this weekend and see if I can actually publish it this weekend. But let's see. It depends on that case, that specific case.
And Professor, if you have a time, can you upload the lectures 10 and 11 on the YouTube?
I
really
sure,
appreciate
yeah. That's the big thing if I have a time. Yeah, I'd try my best to do that.
Thank you so much. Really appreciate it.
Sure. Okay, then if nothing is there, let's stop tonight and see you on next Monday. You have one more programming assignment next Monday, right? Coming up, assignment 5 probably.
Yeah.
Yeah. Please make sure you do that, and you can apply whatever we learned today from high level code to intermediate to the assembly level. That will help you a lot there.
Thank you, Professor.
Okay, thank you.